Good morning to all our attendees. Welcome to Cengrs webinar series, where today we are diving into a depth session of mitigation foundation distress. I am Pooja Dabhal, marketing coordinator at Cengrs and the moderator for today's session. Today, we have the privilege of hearing from a distinguished expert in geotechnical engineering, Mr. Sanjay Gupta, Managing Director of Cengrs Geotechnica Pvt. Limited, with 53 years of experience. He is widely respected as one of the top geotechnical engineers in the country. His expertise spans a wide range of areas, including large diameter board piles, high capacity load testing of piles, ground improvement techniques, and foundation design under challenging soil conditions. Additionally, Mr. Gupta is actively involved in various technical industries committees such as the Geotechnical Engineering Committee of the IRC and the Bureau of Indian Standard Committee on the Foundation Engineering. He has served as an executive committee member of the Indian Geotechnical Society and received prestigious awards for his professional excellence. He has published over 80 plus technical papers on geotechnical field aspects and delivered keynotes and invited lectures at various forums and webinars. Mr. Gupta's commitment to bridging the gap between academic research and field practice, along with his dedication to implementing modern practices in the Indian industry, makes him a recognized leader in the geotechnical investigation field in the country. Before we begin, I encourage everyone to participate actively. Please drop your questions in the chat box and we will address them during the Q&A session. Over to you, sir.
Thank you, Pooja. Welcome to one and all on this webinar. Sanjay Gupta here. Well, I'll start with my presentation now. What is distress? Can be for the project, can be in the foundations of the structure. It is a foundation where geoprofessionals come into play, where we are concerned. And the whole thing is to act as a doctor with a healing touch and not as a policeman. Foundation distress can be as a man-made or natural. Man-made can be as an ignorance of soil, loads, additional loads. Natural can be there may be a well or a pond, artesian conditions, which may or may not lead to disaster or the failures. When foundation distress, various causes. Am I audible? Sorry. Pooja, am I audible?
Yes, sir. Yes, sir. You're audible.
Am I audible?
Yes, sir. You're audible.
Okay. Please let me know in case I'm going too fast or very slow.
Sure,
Okay?
sure, sir. Sure,
Thank
sir.
you.
Okay.
So the foundation distress can be due to the variations in loads, additional flows which were not planned earlier, change in space utilization, change in structural or architectural layout. The soil conditions, the unusual soil conditions, loose soils, unmapped tunnels, localized problems, strata not behaving as envisaged, whatever we had envisaged during the design stage, inadequate soil data, misinterpretation, and or wrong analysis. Importantly, design basis without reference to site conditions like a mystery approach. There's a kind of a situation which one may encounter underground tunnel or cavity, hill slope failures, all of us know about it. Settlement cracks in the walls can be due to differential settlement, not properly designed or executed. Damages due to earthquake. Now, what are the steps for the mitigation of distress, foundation distress? The mitigation of distress says that we have to take the steps before the disaster takes place, preventive action to avoid failures. Experienced engineer can identify telltale signs. You have to ensure desired factor of safety, meet serviceability criteria, restrict further settlements, allow additional loads for vertical expansion as required, facilitate adjoining constructions, which is very common when you are doing a deep excavations adjoining a building in the
Sir,
project.
excuse me, sir. Just a minute, sir. Just a minute.
Yeah, yeah,
I think
sorry.
there's some technical glitch. Just a minute. Do it and slideshow.
Yeah. Sorry for interruption.
I only see the title slide.
Present
I,
again.
no problem. We'll start. Yeah.
Yeah. Do it in slideshow, Tanya.
Is it okay now?
Yes, sir. But we need to do in full screen.
Ara? Now is it coming? There's a
Not
full
in
screen.
slideshow, sir.
Is it okay?
Yes, sir. This your presentation is visible, but the problem is it is not in slideshow format.
This on a slideshow.
Huh. Just put it on slideshow.
Yeah, it is. Is it moving? Just check that. Right?
I don't see the slideshow.
Why? Please inform the participants for a small glitch.
Yes. Please hold on as we have some technical glitch here. So we'll be continuing in 1 minute only. Just wait.
मैम ये स्लाइड शो नहीं हो रहा है
यहाँ तो रहा शेयर में नहीं।
यहाँ पे तो शेयर हो रहा है बट वहाँ नहीं हो रहा ये चेक करो ये
Sir, sir, please unmute yourself. Sir, you are on mute. Sir, you are on mute. Sir, unmute yourself.
Ah, okay.
Okay. Yes, sir. Please continue.
Okay. Am I audible now?
Yes, sir. You're audible.
Am I audible?
Yeah.
Okay.
Okay, fine.
Sorry, participant, for a small minor glitch. You can call it as the initial stage of the distress without a casualty. So I'm back here. I'll continue right from the beginning. Well, as we know, the distress on a project can be due to the foundation or the structure. It is for the foundation where we geoprofessionals come into play. We have to act as a doctor with a healing touch and not as a policeman. Is it visible? Okay, Pooja?
Yes, sir. Yes, sir. Absolutely fine.
Okay.
Yes.
Okay, good. The slides are moving.
Yes, sir.
Okay. So as far as we geoprofessionals are concerned, we talk of the foundation distress. Foundation distress can be due to the man-made or a natural. Man-made is the ignorance of soil, load, additional loads, etc. Natural can be a well, pond, or artificial canals. It may or may not lead to disaster or the casualties. Foundation distress, the various causes can be the variation in loads on the foundations due to the additional floors, change in space utilization, change in structure or architectural layout. The soil conditions, your unusual soil conditions, loose soils, unmapped tunnels, localized problems. When I'm using the word unusual soil conditions, it means that the soil characteristics have not been and we said have not been identified properly or correctly, which leads to the distress. Strata not behaving as envisaged, inadequate soil data, misinterpretation, or wrong analysis. The design basis without reference to site conditions, the engineering analysis, like the mystery approach. These are the certain things which may result into the distress in foundations. Now, this is at one of the sites. It's a photograph for the underground tunnel or a cavity. You can imagine if or you construct something over it, what may happen. The things may go wrong. Heel slope failures, all of us are familiar. The settlements cracks in the wall due to differential settlements, due to earthquake. Now, what is the step for the mitigating a distress, foundation distress? It is the steps which we take before the disaster strikes or on noticing first signs of distress. Preventive action to avoid failure. Experienced engineer can identify telltale signs. Our aim is to ensure desired factor of safety, meet serviceability criteria, restrict further settlements, allow additional loads, vertical expansion as required for the project, facilitate adjoining constructions. Now, this thing is very common in the urban areas. You have a building and you want another person excavates deep for three basements, four basements, close to the existing building. So there will be can be some distress. Sorry. Now the failure versus distress. The actual failure when the structure has failed, foundations have failed. You are able to work the back analysis, and work out the soil parameters to work out the cause of the failure. But in case of a partial failure, distress, serviceability is the problem. You may not be able to do back analysis, so it requires ingenuity of the engineer. Well, now to summarize, that the foundation distress can be due to the settlement, share failure, serviceability. Main issues are always with the settlements, total or differential, and the serviceability criteria. The approach for mitigating the foundation distress is same as forensic geotechniques, but without involving the court of law. If some of you might have attended our previous Cengrs webinar on forensic geotechniques, there we had worked out a few things and elaborated the various steps to be taken. Well, the main thing is what went wrong and why. The four W's is a rule to mitigation. It is the same rule as for the forensic geotechniques. Is it like a brainstorming session? Because this is something where you have to identify, like in postmortem, one does, on the dead bodies. But here we are doing it. My project of the foundation is not dead, but it is approaching to that, and we have to work out a solution. Another important thing is where, when, and how that distress is started. Mitigating foundation distress is as much an art as it is a science. You know what? Mitigating a foundation distress is not a rocket science, okay? But just an understanding of the strata and to work out the issues related to it to come out with a solution. So, moving forward, one has to identify the problem, investigate the causes, assess the risk. I mean, these are the parameters for the four W's. Review structure details and geotechnical data, assess foundation behavior, perform analysis of data. Is a kind of out of the box, the innovative approach. Most of the things you may not find in the books, but you can only take the help of that to work out your innovative approach. So it is the step we take before the disaster strikes, right? It is the preventive action to avoid a failure. Experienced engineer can identify the telltales. Effective solutions can be implemented easily, ensuring a stable and safe foundation system. As much an art as it is a science. I hope I'm not too slow, Pooja, or the slides are moving.
Yes, sir. Everything's
Okay,
fine.
good.
Absolutely perfect.
Right. Thank
Thank you.
you. So I can summarize it in this way. For the four W's approach, you need to understand the geology or the soil strata, right? Then I need to do the assessment for the reasons and nature of distress. You do a selection of investigation techniques to get and understand the more of the soil or the ground parameters. You do the design profile, come to the appropriate analysis. All these things are the four W's. Then you come to the, mitigating the distress. I mean, this is a basic approach what one has to follow. Now, the scientific approach, I can now, come to the more of the, on the side of the engineering, detailed investigation of cause and mode of failure. That is something which we require. Then we need to do the engineering solution for a failure or a potential disaster. Sound engineering practice. So my steps would be to evaluate the substrata behavior. This one comes after knowing the distress, what kind of a distress has taken place. And we are moving toward the failure, right? But not yet achieved the failure. Predict behavior of the structure, assess reasons for distress, work out a solution, implement the foundation strengthening scheme, monitor effectiveness. That's the more important. Forensic geotechniques is the basis for mitigating foundation distress. So one has to understand the forensic geotechniques to work out a mitigation of foundation distress. Now the flow chart would be very simple now. Sorry, summarizing the whole thing. There's a project. Problem is that we have an inadequate foundation, excessive settlements. Now you know to geotechnical data, structural details. We do the analysis, we do the prediction of foundation behavior. Based on that, you work out the alternative schemes, work out the review the merits and demerits, finalist scheme, and then the implement. This is the very simple crux of the whole thing. in mitigating the foundation distress. Now we will talk of the various case studies for mitigating. One thing I would like to mention here for my younger fellow engineers, it is to understand that mitigation process is simple, right? And you have to come out with the innovative solutions. Some of us might have known about these certain cases in the past, but this presentation is basically is an aim for the younger engineers, to understand this. Not a rocket science. It is very simple, but one just needs the understanding. That's all. Well, I'll start with the Janbhoomi temple at Mangar, UP. This is just the model, which has got the main temple here, Garbhagriha. Then you have the small temples, as they call it, as a corridor, and this is the platform. This is done by the architect, temple architect, Mr. Sompura. It's the third generation who are doing. Rather now the fourth one is also come into role. He's the same architect who has been involved with Ashadam temple here in Delhi and also for the Ram Janmabhoomi and various other such temples. This place is the birthplace of Kripalu Maharaj. Some of you might have heard him or seen him over the Asta channels. That was the birthplace at Mangar, near about 35 kilometers from Allahabad. It's a massive structure, traditional ancient Hindu temple architecture, granite blocks up to platform level, then the carved granite blocks, the temple structure. Is a traditional Hindu style, ancient temple architecture. Only stone granite masonry, no RCC to be used. Temple mythology is that only stone masonry because they want all these temples to last for about 1,000 years or more. No RCC construction is permissible. Why? The belief is that the steel will obstruct the divine vibrations between devotees and God. I do not know how far it is correct or wrong, but this is what is their belief. Now come to the structural details of the temple. They have a very standard, the thinking about this kind of the temple construction. The foundations will be at 3 meters, that is 10 feet below the ground level. They will make a total stone block as a huge block. Then the platform will be 8 feet above the ground level, that is 2.4 meters above the ground level. So it is a 5.4 meter thick, massive granite structure. Its own load will be about 14 to 15 tons per square meter of the foundation block itself, right? Which is quite heavy. And over that, the temple has to come the Garbhagriha, which is the highest peak one with the maximum loading, which we will see subsequently. Is that now the main block is surrounded by 4 feet wide peripheral granite stone walls for small temples. Right? When we move forward, I'll tell you that their basic designs were. Now this is what is the loading details for the temple. Main temple is there for 25 to 27 tons per square meter. Small temple, these corridors, I do not know whether my cursor is visible or not. For small temple is 2021 and the platform is a 15-16 tons per square meter. The main important point to notice here is that all these stone masonry things are interconnected, right? There's nothing is known as a construction joint or expansion joints. Is it going okay? Yeah. So the geotechnical considerations, total settlement is never a problem here. Tilting is not possible, not permissible. Why? Because it is of the stone masonry total one. So they don't want any tilt to take place, otherwise the joints will open up. Here I get reminded of another case in Warangal, near Warangal, known as a 1,000 pillar temple, as a what of the very, very old one. Then what had happened with the passage of time, there was a certain differential settlement and some of the joints of the beams and the pillars, columns as we call it, got, disjointed. So with the result, the temple was having a distress and that was yet showing the signs of cracks and other things. Well, in this webinar today, we are not going to talk much about it. I'm just telling you some example. But next webinars, following webinars, we'll try to cover more of them. So take from this is that the differential settlements are to be minimized because of the joints of the stone masonry. Now, dome type of a structure, in the gray and also the mandap, it cannot withstand tilting. You will understand and appreciate that. We have these loadings, which we have already discussed, variable loading. So whatever you may do, right, unless until the foundation system is properly designed or executed, you are going to have a differential settlement resulting into the tilt or onto the cracking of the system of the stone masonry. Now, incidentally, the problem was noticed when the cracks were noticed when the test was done up to the 2.4 meter plus level at the top of the platform, okay, with a loading of approximately 15-16 tons per square meter, even before the construction of superstructure began. Engineers opine differential settlement tilt is critical under very loading conditions versus the soil characteristics. The limitations what were given to us were that no steel should touch the temple structure, no steel to be used in mandap area, limited work space for additional foundation, no RCC for taking tensile or bending stresses, basic structure not to be altered. Right? Now these are the limitations given to us. We started with the evaluation of the soil conditions. We did, depending upon the availability of the test locations, because you would appreciate that 3 plus 2.4 5.4 meter thick granite blocks are there. Fortunately, whatever their architectures, I will show you in the subsequent one. We could do some 4 bore rules and static cone penetration tests and 2 plate load tests. And we worked out that the net allowable loading intensity is of 14 tons per square meter only for 100 millimeter of the total setting. Now, here we are not talking the differential, but this loading intensity of 14 tons per square meter is simply not sufficient to support these structures. Now, this is what it is. This is here is the platform. This is that, the main temple, and this is that mandap, and here is the garbhagriha, this one. And all these corridors, what you are seeing, the lines are for the small temples, right? Where they have, the library and so many other things. This is the foundation detail which you can see. It's a complete, the granite block one, 3 meters and 2.4 above, where the construction was on hold at that point of time. You will appreciate that here, because of whatever they had the thinking, but here in the main temple, these are the spaces which were available to us as a free. And these are the walls, 1.2 meter wide walls, 4 feet wide, which are coming right from the bottom, from the -3 meters below and coming straight as a vertical one. To tell you, here it is like, the vertical walls. No spread, no foundation below that. It is a 4 feet, the complete walls. This is what is the soil strata. You will find that the water table was encountered above the foundation level. The foundation was at 3 meters, so it was less than above the 3 meters. These are the end values, and the soils are the sandy silt predominantly, and the clay silt. Incidentally, what had happened, and this is a kind of a plot for the SPT results. Of course, the sum which we had done from the top, and this is the foundation. The values are fairly low. Even the end value of 10 one could find only below about what? it is at 23, and say the below the about 5-6 meters below the foundation level. Static cone penetration test also indicated the same thing with the QC values at the low values. Incidentally, there were certain spikes for the higher QC values, like this one here, right? Otherwise, this is the value of 40 kg per cm square, which is on the lower side. So our solution we worked out after the too many of the discussions with the team and the number of the devotees comprising of the retired ENCs of the various departments, top chief engineers. We had a long discussion. Our summary was that one need to do a confinement to the main temple so that the temple, the soils below the temple area, the main temple, they do not try to squeeze it. Restrict outward flow of the soil, reduce chances of tilt, improve soils around the small temple corridors. As I just explained, the small corridor, the temple corridors are only the 4 feet wide, the vertical walls, okay, without any kind of a foundation that we understand as the geotechnical engineers. So for confinement, we came out that we have got no other solution but to go with the RCC board piles with interconnecting beam for lateral rigidity. Right. I'll come to it, what was the issue with the using the RCC board piles subsequently. For small temples, we proposed for the ramped granular piles or stone columns to densify the strata to transfer the high loads to avoid shear failures of the punch. The main issue was in the mandap area. Mandap is an octagonal opening in the center of a big dome, supported over only the 8 columns. Now, by the way, these 8 columns are only by stone columns. The whole problem here was, there's a huge one without any reinforcement or without any, the tensile stresses. This soil of the, which is inside that octagonal one, may squeeze and may move up due to the lateral load pressures as natural moisture content of the strata was fairly close to the liquid level. Now this is where one has to understand why this thing will happen because and no RCC piles could be used in this area, right? Because there's the mandap is the main area. So the decision was to provide the plain concrete piles to confine mandap area with a concrete slab, not RCC, on the top, just to make it, the soil is replaced by the concrete, you can say. Now the confinement for the main temple to create cutoff wall, as we had discussed, to make, the pressure distribution more uniform, increase bearing capacity, safety factor, restrict the lateral soil movement, restrict differential settlement, ensure total settlement becomes more uniform in a more controlled way. So, depending upon the space, as I showed you in the earlier one of the sketches, we had only about 500 and in some places 800 thick, wide space only around the main temple, where the 2 stone masonries were done. So we could only adjust the 400 dia pines to go about 9 meters below the foundation level. Pines are cast 700 below the platform level, provide interconnecting beam in annular space, keeping top of the beam as 300 below platform level. I'll just show you the sketch. So this again another stone masonry which is coming. So this is what the space we had, where we had these, the RCC piles, okay, all around. The idea of these RCC piles are that this will do the confinement. So with that loading of 25 tons per square, if there's a settlement and it should go uniformly, not to tilt, and this soil should not get squeezed out. Now, RCC of beam and stone masonry was separated by shell export. Their guideline was no RCC should touch with my stone masonry, my original temple structure. So we provided a shell textbook to create that, and the open space covered by the granite slabs, maintaining air gap between RCC beam and the stone masonry. So there is a air gap. Now we come to the mandap area, which is the most important and very critical because of this octagonal shape. Each side of about 10 feet, that's about 3 meters wide, supported only by 8 columns. It is highly sensitive to any differential settlements or the tilting. What we proposed, as I explained earlier, we did the 400 dia concrete piles without reinforcement, right? No steel, only the concrete piles. But it was not possible in such a small area to, excavate the whole thing out and fill back with something. So we tried to, fill it with the concrete piles. They have another thinking that if the construction has already begun and after that you want to start dismantling or taking out something, then it is a bad indication. So they have their own, the Maharaji had his own concept. He said, I don't want to do anything. You tell me to remove all the blocks and do anything. No, it has to stay here because the puja has been performed. So one has to live with all those things. So we had these piles, concrete only, no RCC, covered with a concrete slab with the gap here to provide the shell text board here. And the top there is a gap, air gap, so that we can have to mine now the slab will come here and we will maintain the gap. Now comes the small temples corridor. The strip footing, as I mentioned, 4 feet, that is 1.2 meter wide. Loading is 21 tons per square meter. Now, looking at the soil characteristics, you would all agree with me that a 4 feet, 1.2 meter wide as a vertical wall under the loading of 21 tons per square meter will have a shear failure or punching failure. Mind you, there is no enlargement at the base. It is just acting as a 1.2 is the foundation size. Settlement will be excessive, underloading. Now, there's differential settlement due to variance in the rigidity, stiffness of the structure. Why? Main temple has a different behavior, small temples, and the platform. So, all the three are moving in the different directions. For the small temples, what we suggested for the granular piles of the stone columns, the concept is the composite material, my phi value, angle of internal reaction would go to 35 to 45 degrees to avoid a punching and a shear failure. Compact soils around the strip footing, improve the bearing capacity, reduce settlement under the loading of 21 tons. Whole idea is here my loading is only 21, but in the main one it is 25, 26 tons per square meter. So we wanted to create a compatibility with a main block to reduce the differential settlements. So granular piles of 500 dia were provided 5 meters below the foundation level, and it is provided 1.5 meter above the foundation level, that is 1.5 meter below the ground level. Okay. Sand filling compacted above the stone columns up to the platform level. Now this is the kind, these are what the brown color things are the walls, 1.2 meter wide one. And on all the sides, whatever the space is available, we try to fill it with the granular piles or the stone columns. Basically, it is a replacement concept. Here it is, as I just mentioned to you, that it is, going down below 5 meters below the foundation level, okay? And up to here, and you fill it with the soil, and on the top of the platform, then you have your platform slab. So this is what I have already explained within this is the overall scheme now. This is the mandap area, right, where we had the RCC, only the concrete piles. This is the main temple, Garbhagriha is here, which has got the highest loading here as compared to the loadings of the other part. And this is what we had all around the open space, the RCC piles connected with the RCC beam, separated by shell text board and with the air gap of about 200 to 300. This is the typical arrangement for the small temples. These are that 1.2 meter wide, the vertical walls. We had the ground improvement by stone columns here, 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 all around, just and similarly on this side also. So this is how it was done, and this is the view of your small temples after the construction. You can see how they are. There's another one. This is the view of the fully constructed temple. This is the ground. This is the platform level, which is 2.4 meters above the ground. This is the main temple. This round thingy is the mandap. This is the garbhagriha. And these are the small temple corridors. It is done, and no distress is observed in the last, I think, over a 25, 30 years. Now, next I take pardon, the tilting of overhead tank. There's a well, we start with the 4Ws. Overhead tank of 30-meter height. It has got a cyclic loading, as all of us know. The water tanks always have. The daily you have a filling and the emptying the tanks. During hydro test, slight tilt was observed. Designs were checked and found okay. Investigations were carried out. Inferred soil strata is responsible domain of a geoprofessional. I mean, it's always the case, if there is any distress, the structural engineers, the project will say it is the ground which is the culprit, nothing else is wrong. Our quality, everything is good. Well, as a geotechnical problem was to understand what went wrong and why. We start with the basic concept. And it was observed that under the tank, on one side we had a raw rock, hard strata at 4 meter depth, and the other side was a 6 meter. And in the top it was a loose sandy silt with the end value of 8 to 10. So it was very clear to us that because of this, the thickness in the compressible layer, there is a differential settlement. And by the way, I think I have another slide to show you. Uh, 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 yeah, here it is, okay. And on this rock, because as per the geology of the neighboring area, there was a water table is there. So with this slope, the water was tending to flow in this direction. Okay. So that was another reason. I thought that I had soil data also. So here the idea was to, how to do the strengthening. We suggested to create a curtain wall as a confinement to restrict lateral soil movement and control migration of piles. Combination of closely spaced short piles seated on underlying hard strata and a cement grouting of the looser strata soils. Now this is what it is. This is the overhead tank, right? The RAF foundation is 8.5 meter, 8.5 meter diameter. There's that time the tilt was observed on this side, right? Tilting. Now you will appreciate that the tilting was on the side where my soil depth to the rock level, to the refusal strata, is more. So I have a higher thickness of my compressible layer here as compared to the left hand side. So this one tells you that we had, the grouting holes, we had the piles as a confinement. This is what it is. I'll explain you in the next slide, maybe in a better way. Yeah. So this is the time we had, this is what is the edge of the red one is the edge of the rock foundations. We had the grout holes, we had the piles. Okay. Idea here is only to make the confinement. Whatever the tilt has taken place, I cannot put it right. Okay. But as per the structural consultants, designers, that much tilt was tolerable for the stability of the tank. The tank will not overturn. With that one, our idea was that no further settlement should take place, differential settlement with the passage of time. Well, in the first phase, we had the diameter auger pile, 300 auger pile, which could be done, up to the refusal strata, whatever maximum. You know what we did after the reinforcement place? We put a PVC conduit pipe, okay, up to the bottom where we wanted to do the grouting. Okay. Now after this concreting or the concrete pipe was done and the grout was pumped through the grout pipe. After about 24 or 36 hours, we wanted the concrete to be set. In the second phase, we had the grout holes of 75 diameter were drilled in the space between the piles and the raft foundation up to the refusal. Grout holes were plugged and pressure grouting with cement slurry was taken up and till the refusal to intake of 2 to 2.5 kg per centimeter square. The idea is that this cement slurry, the pressure grouting of 2 to 2.5 kg per centimeter square, will also solidify the soil moves and the lateral all around the piles are going to provide me the lateral support. So confinement, right? So under this loading, this soil will not be able to move outwards and it will have a uniform settlement if at all required. No further distress still noticed over the last about 35 years. So we are successful. Now I'll take up one more case of the foundation strengthening of a residential complex. You'll appreciate that all these things are coming, but slightly out of the book, textbooks. Is a complete residential complex, four-story residential block? No, it was done and they were all safely standing, no issues. But during the excavation for services, they observed that the foundation were extending just beyond the wall widths and to shallower depths, means the proper design was not followed. When this alarm was sounded, other wall foundations were checked and it was found that all the blocks, there were what, if I'm not wrong, about the 12 tower blocks, that the less foundation widths and the depths are observed throughout. Though the structure was not showing any distress, but factor of safety was lower than the required. Secondly, these kind of the structures cannot be given for with the certification of the safety for the occupation, for the residents to stay. So this is what is the typical strata. This what at a 3 meter we got, at some places 6.5 meter, and values are fairly okay. So with the result, even the simple wall foundation, without any spread, without any foundation as such, were able to withstand the four-story load. And it is a complex with the load-bearing walls with a few columns, spread footings as per the design, but not executed. Allowable loading intensity is on an average of about 15 tons per square meter onto the foundation design. So we had to evaluate the foundations. At several locations, small pits were excavated to measure the actual foundation sizes. Right. Suppose my actual requirement was say 1.5 meter, but we were finding only say 0.4. Now with the loading data, you can calculate that what is the actual bearing pressures were computed. Okay. Then you compute the factor of safety was ranging from 1.3 to 2, which is less than the factor of safety of 2.5. Right. By the way, it is a government project, so nobody is going to sign the document with a lesser factor of safety. Various solutions were reviewed for supporting the structure loads by additional foundation system with respect to merits and demerits. The one of the suggestion was to do the underpiping, which was rejected. Another one was by providing ISMBs. In ISMBs, the theory was that just below the plinth level, the walls shall be, the extra dismantled. You put a one ISMB on this side, then on the other side you dismantle and put another one. So that, but it was not feasible. It was not safe at all. The way the work you do. So after a lot of debates, we came to a final choice of a pile needle beam system. I'll just show you how it is. Providing piles on either side of the wall, connecting piles by a needle beam over the piles and through the wall, concreting and grouting the gap between the beam and the wall. Okay, provide rebar in walls up to 1.2 meter height above the plinth level to exert beam for distribution of load. Simple theory, no rocket science. This is what is a sketch. This is the one how they found it. Say this is a one typical case. So we could have a 300 I3 and all these piles were going up to the hardest strata, right? Now connect by this beam, needle beam as we call it, and in this brick masonry we do up to the 1.2 meter height we do the chasing and provide the one rebar in the wall itself. So idea here is, and this gap when you do the needle beam, I'll show you a sketch. This is the steps, of course. I'll go first through with this. The wall pits we excavate to measure the existing foundation. We calculate the load that can be transferred, based on the bearing capacity, compare with the structure loading, compute the deficiency in loading, and design the spacing of the pile group to meet the deficiency. This is how it is. This is the needle beam, and when you are doing this kind of a dismantling, you cannot do it very uniformly. And mind you, it was to be done only manually. I mean, no pneumatic system. A four-story building is standing. And we do the grouting. You can see this one is a completed one. This is the grouted, so that this wall is touching the beam. So the loads are getting transferred to the beam and then to the piles. This is a typical layout. You can see the various loadings on the walls as was provided. And we had these two piles, one on this side of the wall, one on this side. And you do it. Similarly, for the columns were taken care of. When housing complex was handed over after the strengthening, all houses are under occupation. No. Yeah, am I audible?
Yes,
No
sir, you are
distress
audible.
or cracks have been observed, and the structures are there for over 35 years with desired accuracy. In fact, what the people say is that these houses, after the strengthening, are much more stronger as compared to the earlier ones. And here, just to mention of the record, some of the people have done the extensions. Because over the fourth one on the terrace, they have constructed another structure and the extended balconies and everything, but nothing is going wrong. I'll take you quickly to another equipment foundation of a power plant. Uh, yeah, I think 10 minutes more or so. Yeah, Pooja?
Okay, sir.
Okay. So this is a thermal power plant in eastern Uttar Pradesh near Prayagraj, near Allahabad. In these kind of the plants, you have the various small equipments, pumps, foundation, and they which are placed on the backfilled soils adjoining to the TG. TG foundation was seated on rock at about 8 meter depth. This whole is the situation. So the equipment foundations, when they were providing onto the grade slab or a floor slab, what it was done is that we thickened the floor slab where the foundations were such foundations or the such equipments were coming, right? Designed for a very low loading intensity of only about 4 tons per square meter. Now, all this because with the TG foundation, you have a deep excavation, right? And you require a certain slopes. So it was on the backfilled soil, so which extends to about 3 to 5 meter depth. The filling extent was higher adjacent to TG columns due to the depth and slope, as I just explained. The presumption was that compacted fill can withstand such loading intensity. I'm sure that nobody has kept any control and the what we call it as engineered fill to control the compaction levels. However, looking at the issues, the compaction was not it was inadequate. The Filling was poorly compacted, especially adjacent to TG columns. Reasons not known to us. Several foundations settled even before the equipments were made operational. Major settlements range from 16 to 180 millimeter. Now you would appreciate that any equipment or a pump with these kind of settlement will result into, all these pumps and the equipments are connected with some other features here, like the pipelines and other things. So with this kind of a settlement, all my joints are going to open up. So it is not going to be workable. Incidentally, as evident, higher settlements were observed towards the TG side foundation, where the filling was more as compared to the other side. That's quite obvious. Cracks were also observed in the nearby paving slab or the floor slab due to differential settlement. Is all the result is due to the improper compaction of the backfill. Well, this is the something, a foundation width are less than 3 meters. Design was for 4 ton per square meter. These are the kind of settlements which were observed. Minimum is 16 and the maximum is going up to 193. So we have the issue. Well, the distance is just the photographs. You can see the distance here. You can see the tilt here. So the problem statement was the foundations are placed on inadequate. There's a possibility of further settlement during operation of equipment. Naturally, when the equipments run, they generate additional load and the vibrations. The foundation that had not settled may also experience settlement in future. Stabilization of foundations that have settled as well as the preventive action for other foundations. So this is what is the crux now. Well, this is the kind of the data, and you can observe that the kind of the N values 1, 2, 1, 2, is showing typically a very, very loose strata. That means it has not been compacted at all, I would say, not even the word properly. So the restrictions were the equipment cannot be dismantled due to the site constraints. You can't dismantle the power plant, so many equipments. Movement of any kind of heavy machinery was not possible due to the headroom and so many equipments. So normal ground improvement techniques were not feasible. Further settlement of foundation has to be restricted. So the solution has to come, the out of the box solution, as I mentioned in the initial slides. So options we considered was as a cement grouting of loose soil and a micropiles and the combination. I'll just explain you how it goes. So before going into the, as a work, as a project, there were a certain trial runs of the grouting which were done to, ensure that what kind of a thing we are able to achieve with the grouting. Again, it was, under the steady pressure of 1.5 to 2 kg per centimeter square. And it was, these are just the photographs showing you the grouting part. Well, the method is very simple, as all of you know. Trial grouting was done to form the grout curtain. Okay, it is a soil. You drill the hole of 75 mm at top of the rock. We have a conduit pipe, a steel tray, and a concrete plug at the top, and then you pump in the cement grout. Okay. Till the diffuser to intake to around 1.5 to 2 kg per cm square. Now, while we were doing the trial grouting to estimate, we found that there were certain places the large voids. Adequate pressure did not build up even after pumping large quantities of grout. Grout was flowing in an uncontrolled manner, resulting in no significant improvement to the soil, right? Now, this is what, when you go, one has to go step by step to see the adequacy of the one system and then to supplement something more to achieve your goal. Therefore, grouting adjacent to the foundations was not a sure shot techno-economical solution. Then we came up with another idea of the micro piles. 150 dia piles, RCC board piles extending to top of rock. Concrete flooring had to be cored using a diamond core cutter, otherwise you cannot do the auger boring. After boring, we put a PVC pipe into the hole and reinforcement cage was placed. Now somebody will ask me in a 150 dia pile how you can provide the reinforcement as per the codal provisions of 8 miles. So I'll come to it. Concreting was done using the small size stone aggregate of 10 mm. Reinforcement of pile was bent and welded to the reinforcement for the floor slabs and the other foundation whatever. Now the skin friction of the loose soil was ignored. Weathered rock was treated as a dense sand with a phi of about 35 degrees to compute the end bearing. Pile compression, you calculated each pile was designed for a carrying capacity of 1.5 tons only. Total of 511 piles of 3 to 4 meter, depending upon the rock depth, were installed. Now here it is, when you do a pile of 150 dia, we had a very limited number of reinforcement, okay? And because we wanted a kind of PVC pipe also, the conduit pipe also to go through it. Why? Because the base of these piles, whatever you may do, there would be a certain gap, the gap between the hard or a rock strata and to the pile tip. So we wanted to put a pipe and grout through it also. Then this is the slab. When they were doing the coring, it was observed that there here below the slab also there were voids. So it had to be filled with the cement sand slurry, okay, to fill up this. And when you do this, you cannot start the pile boring, though it is an auger boring, you cannot start immediately. You have to give a time gap for this grout to settle. Then another issue was to fill the large voids. Beneath the slab were filled with cement sand, as I just mentioned to you. Pump cement sand slurry beneath the slab to fill the voids. Right? Restrict water seepage, reduce permeability and compressibility, and enhance shear strength. So all around this building, there was a plinth protection and a drainage system. We don't want any water, any rainwater to go into the substrata. Well, with this one, I'll come to the conclusion. Mitigating foundation distress. It is a step prior to the disaster or a failure. Like, any human being. Rather than waiting for, the person to die, we start taking the preventive and the mitigate the problems. Approach is similar to human body, the same way. I think whatever we have been talking, it is the same. Is a diagnostic approach, 4Ws. Same thing like the human body. You have to go through the history, you go with the pathological investigation. Then the treatment, you start with the treatment, you check the response. Okay? Absolutely the same. Consider a project or a foundation system as the human body. You consult a geoprofessional as you would consult your doctor. Well, yeah. And I would say that the forensic geotechnical engineer has to become one with the soul of the foundation system. Be a part of the soil, feel the stresses, deform along with it the solution to the problem will emerge from within that soil. At this point of time, I would like to say something, especially for my younger engineer friends. The main point to take home here is, at the first place, do a proper geotechnical investigations, right? Assess the substrata conditions, do understand the performance requirement of your project, whatever you are going to construct. And you should do a proper analysis. More so, it should be a proper execution, right? If you are doing a backfill, it should be a properly backfill, properly compacted backfill, as per the requirements. So if any action is taken, the post-distress, you will agree with me with all this, only the 4 case studies. The owners have spent a lot of more extra time and the money and the energy and the delays in the project, right? Which could have been avoided in the initial stages if one has understood the problem, understood the substrata condition with the right kind of geotechnical parameters and analysis, one could have solved this problem. You can avoid so many things, right? Well, I would say geotechnical engineering is a science, but it's practice and art. Thank you very much. Stay safe and healthy. Take care. Namaskar. Over to you, Pooja.
Thank you so much, sir, for such an insightful presentation. Now it's time to move on QA session. I encourage everyone to keep posting your questions in the comment section and we'll address them one by one.
Okay.
So, sir, today's first question is from Nagesh Madapura. Were the piles in the periphery touch piles?
Sorry. Say again. I missed that.
Were the piles in the periphery touch piles?
In the main temple, yes. They were closely spaced piles. Now, I will not call it as a touch pile because of the sandy soil. There was a collapse. So they were closely spaced. If I'm not wrong, I mean, I don't know whether I've shared that. The 400 IRCC piles were at a center to center spacing of what? 500 or so. Does it answer?
Yes, sir.
Does
Yes,
it
sir.
answer?
No, sir.
I'm not able to read the chat messages. I can't read this.
There is another question from the
Ha.
same person. Why grouting was not an option in the temple rehabilitation job?
A very good part, very good. You see what? These temples, as I mentioned to you, these kind of the ancient architecture, they talk of 1,000 years. They don't talk of 30 years or 50 years. And with such a heavy loadings, it was not opined that a grouting itself will take care of such a varied loading intensities. If you have in the Manda 27 ton per square meter and the platform is 15, 16, which are just touching each other. I mean, there's a part of that temple, if you recall, right? So you cannot have it. So stone aggregate being as a hard one, and by the way, here this stone aggregates were of the granite, whatever the blocks they had and whatever they had the cut pieces, from there only it was this man, crushed and given to us for the work.
Thank you, sir. And Nagesh also thanked you.
Thank you, Nagesh. I hope I could explain things better.
Next question is from Praveen Kumar. Understanding the criticality of Janbhoomi Temple's foundation, why not the consolidation, permeation, grouting is not recommended?
Very good part. It is that my answer remains the same as just to the previous one. I think, Praveen, you would agree, and I think we have done in okay. Or if you have any other input, please do give me. Incidentally, what the lesson we have learned is the temple, kind of the architecture team and the temple guy. After this manga, after this facing this problem and we solved it, whatever we did, after whatever the further temple they had, they were planning or constructed, they've all gone into the detailed investigations and the proper foundation concepts. So, like in the Vrindavan, Mathura area, I think there are another, at least we have been involved with about maybe a 15 or 20 temples. There are no such issues now coming up, where it has been properly engineered.
Sir, Praveen has one.
Praveen, does it answer your point or?
Maybe, sir. He will reply soon. He has one more question. Like, also, please comment on the buckling of the piles and micro piles while soil pressure exertion.
Good part. Which project are you referring to? Are we talking of Mangar or other?
We will wait for his reply. Next question is from Balendra Molly. Which software used for analysis for finding how many piles required? Maybe how
Good
many
part.
piles?
No software. 40 years back, the softwares were not that common as they are in today. It was done only basic concept was to create a confinement for the whole thing to, go down uniformly. Idea was to avoid the tilt of the main temple and the soil to get out under the loading condition. Lateral flow of the soil was to be confined. And the number of piles, etc., I think in one of the slides is there. If you want to, we have to go back and see.
Sir, Praveen has
Again, answer is the same. No software, right? Those days, no softwares, but we had a limited space. The idea was only to create a confinement. That's it.
Thank you. Sir, Praveen has answered the previous question. If steel is not permitted, why not use geosynthetic?
Very good,
And
very good, Praveen. Now, if the same kind of a situation comes in the last 10 years, we could have, handled that part. 40 years back, I think, I do not know your age, but geosynthetics were not at all born. Not born in the sense of the industry. 40 years back.
Sir, Nagesh has one more question. What would have been the right solution at a design stage in the case of TG foundation rehabilitation?
I think at this particular part, I should not comment on it, right? Because it's a power plant project. The designers were there, they have done it. As I mentioned, the whole issue is with the backfill of the soil, it was not compacted. Because this is what was our finding when we got involved. So I will not like to comment on to the design part because it was done by the experts, power plant experts, so I will not comment. I can only say why this issue occurred, why the problems were there. It was because of the poor quality of the backfill, compaction of backfill.
Kishore Gurnave has asked, Sir, was the four-storied project as Basant Kunj? Maybe his
Yes,
question.
Gurnani, you know it. You've been to the site also during those days.
Next question is from Shruti Anna. Sir, is there any alternative to monitor foundation distress?
Why not? You see, the one thing is that if it's a settlement, how to record the settlements, differential settlement. But the whole problem is when will you go for it? You will only go to see and monitor the settlement when you start to see the cracks. The whole problem in our system is today a geotechnical engineer or a geoprofessional is always forgotten once the foundations are done up to the ground level. Nobody even remembers their name, who was involved and what was done and what was his finding and what suggestions he had given, right? Nobody talks about it. The main starting point would be to have with the settlement is the first criterion. Before you can see the cracks in your superstructure.
Thank you, Nagesh. Thank you, sir, for answering the question. Next question is from Minakshi. If such a situation would arise today, what kind of geosynthetics would you recommend to be used?
You know what, Menashi? Any mitigation process of foundation distress or any root distress is not like the one aspirin. For any disease you have just the aspirin. Every situation, why it is happening, the 4 Ws, right? Remember, the 4 Ws is the main thing. You have to work out the what went wrong and why, right? Based on that only you can work out your any kind of a geosynthetic or any other thing.
Thank you, sir. Thank you, Praveen, Kishore, Shruti.
Stuti,
We'll take the last question of today
okay.
from Manjeet. What is the role of cone penetration testing in evaluating differential statement potential and sensitive projects?
Oh, very good. Very good. We are doing it day in and day out. With a cone penetration testing, starting whether you use a mechanical cone or electric cone or a piezo cone or a seismic cone, you can work out the variation in the strata resistances. Based on that, you can also work out what is going to be the differential settlement because you can calculate the settlements at the different point and you know the differential settlement. And rather in the sensitive projects, by This not the mechanical cone, but electric cone penetration with piezo cones are quite important, and I think they are being used effectively in the industry today. In most of the projects, we are involved, we are doing it.
Thank you for answering the question. A big thank you to all our attendees for your active participation and engaging questions. Before we wrap up, please mark your calendar for our next webinar on Introduction to Seismic CPTU, scheduled for July 19, 2025. And stay tuned for more details and feel free to connect with us on social media or via an email for any further questions. Thank you so much. Thank you, sir, for your in-depth knowledge of on all these questions and sharing your knowledge with all the audience. Once again, thank you for joining us today. We look forward to seeing you in our future events also. Have a wonderful day.
Yeah, thank you, Pooja. Thank you, everyone. But my humble request to all is, with the folded hands, I would say, why should we wait for a distress in the structure or in the foundations? Let's do a proper investigation, proper analysis, proper designing and execution to avoid these things. Uh, Right. Why wait for it? Or why, ignore something which we know should be avoided? And I think, Apuja, we will have maybe a one more session onto the mitigating foundation distress, because here we could only talk about 4 cases because of the time. We have so many other cases to tell you, again, the 4 Ws, what went wrong and why. Yeah, this is something which is affecting the whole industry today, right? With this, thank you everyone
Sure, sir.
to be
Thank you
with
so much.
me. Thank
Thank you,
you.
sir.